All right, so we'll just wait a minute and then we'll get started. Thank you for inviting us back again today so we can deliver a presentation on our NX manufacturing solutions. And today we're going to go back and focus on the manufacture of the tooling that's used for your molding of your consumer products, as well as highlighting the advantages. So with that, let's kick it off. In today's agenda, we're going to cover an overview of NX CAM and then cover reducing the time it takes to prepare your customer data. As you would express, this takes a lot of time and effort to get that prepared before you can put toolpath on, along with showing you all of the capabilities from our 2.5 through 5 axis surface machining on the typical mold insert, in this case a core insert, and then automated programming. We had discussed that you'd like to automate a lot of your plate work. And then the integrated turning solutions. We know now you're using Delcam, you use PowerMill, and then you have PartMaker for that, and you have difficulty with just the integration, two different interfaces, etc., when we're looking for a new solution. And along with ways to improve your ECO and improving that throughput, thus reducing the time it takes to execute an ECO. So let's get started with our overview. So here we see what we call our model-driven process. So let me explain this a little. So as we see over on the far left of the screen, that's our design model file, which can be anybody's data. It can be SolidWorks, Solid Edge, NX data, CATIA, whatever. It's just design data that we can bring into the process for manufacture. Then we go through our job preparation cycles where we can create different stage models for the part for different operations. And then the setup, which you can get your setup assembly drawings. Then on to programming, and all while this is going on in parallel, you can have someone else working on your in-process drawings or your inspection drawings. They could also be doing the setup drawings after we reach that phase, and the shop documentation and tooling requirements, along with operating procedures, maybe even CMM. And then, of course, the execution out to the shop floor by posting NRDNC. Is available in modules, right, along with bundles or packages. But this covers from 2.5 axis milling through 4 axis turning to 3 axis milling to 5 axis. Along with feature-based machining is included in our 2.5 axis, wire EDM, and the turning modules. We call this configured best-in-class solutions. So with this we have NX CAD assemblies, the full CAD assemblies to let you build all of those tooling assemblies that go with. So you have safety and understanding where the clamps and fixtures are, along with material feeds and speed library, shop documentation, and the ability to create and edit your own post-processors, along with download them from our library. We also have material removal visualization. It's included in all modules. Along with manufacturing tutorials are included to get you up to speed quickly and easily, along with a large list of file import. There's over 25 different file formats we read and write. Okay, here we are in NX, and we'll show you how we get started. So this is really our resource bar that shows you there's our tutorials in the beginning, so you can go through and look at any of these tutorials. They're available all the time. So let's open up a part, and of course you can see we open up SolidWorks parts, and of course if we open up NX parts, we can open up any of the formats that we insert. So let's get our core insert that came from your vendor. So there you see we brought it in. It's just a single solid body, otherwise known as a dumb solid. Then we're going to create a setup file for this, which is our manufacturing setup, which is really an assembly of parts, components. So there we're going to pick our general setup. Now we have that. And let's go ahead and look at different orders. There's the tooling order. This is the geometry view. So let's go ahead and identify our workpiece and our stock and our blank and where our machine coordinate systems would be. Right? So that would be where we do that. But we're going to show you something a little different here for a second. Let's go ahead and get our stock body for that. And we'll show you this from an assembly. So we'll bring in our stock. Maybe you got your insert blanks. And then we can put these together. So we're going to move this one first and just kind of have these scattered out there to show you. There we go. All right, go back and get our vise, right? Because a machining job, we have to hold it somehow or other. Lots of CAM systems, you can just throw toolpath on the part. We can do that too. But this really becomes an advantage for us because of clearances. It helps for safety and repeatability for the job, for how it was set up, and helps the setup guys do it. All right, so there's our parts. Let's talk about assembly constraints here. So now we talk about how we put parts together. And for the stock, I can just say these two parts go together and always track those corners. So that's one pick, quick and easy. And then the other one we'll say is, we call it touch align. It's a lot like saying these two parts go together. So we'll say our vice stop and that face have to touch. And then we'll come back and say that the bottom of the side of our vice jaw rather, and that side of the part has to touch, and then the bottom of the part fits, to the bottom of our notch in our vice jaws, or we may have pre-machined those. Okay, so then we'll pick those two. There they are. And then we can go through and start identifying maybe who's our workpiece, where we want the machine coordinate system here. So we'll do that first. In other words, your G54. So there we'll pick 3 planes. I'll pick this plane for my x-axis. I'm going to move it down. There we go. That plane for my x-axis. Then we'll go over and we'll pick that side. That's my y, and that's my z. And of course, then there becomes your G54, your 0. Who our stock is, or our blank that we want to track. All right, now that's the finished part, but in surface machining we would like to not have to always jump over those surfaces and bridge their gaps. Of course we can do that also, but sometimes you want a really good clean, or most of the time you want a really good clean surface. So we use our synchronous technology to do that. But first I'm going to make a copy of this part, and this is the original customer part. So anything I do afterwards, I'm going to make another copy of this part. So if that first part changes, that customer data changes, my 2 operations on the part, first operation for the surface machining, second operation for the little slots, etc., everybody will update if that customer part changes, even as a dumb solid. So I just renamed both of those Op1, Op2. This looks like Operation 1, but to make it Operation 1, again, like I said, we're going to use synchronous modeling or synchronous editing of the features. And by context sensitive is we're going to look for faces, but more importantly faces, we're going to look for a kind of face. And that kind of face is going to be a slot. So if I just pick one edge of the slot, it keeps finding those all as slots, and it closes those. It doesn't create patches. It actually understands the topology of the part, and there you go. You see it's smooth. There's no patch edge boundaries. Now let's go ahead and close the 2 little pockets up there. We can close those off. And again, it just gets absorbed into the geometry of the part. Again, all these small little slots out here kind of would wreak havoc when you're trying to go in and machine that or finish machine that. Right, so you'd be picking all kinds of edges and things. Well, this way it's really quick. We just take those 2 and it closes all of that up. And then we'll go back and do the same thing, and I'll close those other 2 up. So you can see this in real time. Here's quick, right? It doesn't take long to do that, to end up with a very smooth surfaced part that in the end is going to reduce our picking and have smoother surface finishes. So I'll make one other change here real quick. I'm going to change the color of the part. So we faces, that's within my work part. I can just highlight it then, and then we can change. I'll just change this color. You don't have to change the color, but it's just I like to have different color changes. So if I know which part I'm working on, I can tell it just by the color. So that's my first operation part, right? So we're going to tell him he's first op. He's my first work piece, however you'd like to say it. And now all we need to do is go create some operations. For right now, let's just hop in there and say that we want to do a cavity mill operation. We're going to do it on the workpiece, right? And we're going to also then follow that mill roughing. This just sets our stock values, etc., our step overs, and our general depth. So let's go ahead and get some tools. These are coming from our tool library. All right, so you can just search the library. I'm going to search for a library for 20 millimeter tools. So I'm going to pick that. There's a whole bunch of them, and really the difference on those is the holder types. All right, so you can take a look at different holder types and configurations. You can have those named for a specific machine, etc. So now we're just going to go through and say these are the faces. I'm just going to window over everybody, and those are all the faces that I know I have to machine because my insert blank was machined with the shoulders. And that quick, there we have cavity mill. If we want to change that path, instead of following the part, we go around and follow the periphery of the part. Right, there you go, a little more circular type path. And of course you have trichordal and zigzag, many different options inside of there. Of course you can set all your speeds and feeds and depth per cut, just like any other CAM system. So there you go. And you see the roughing. Now we're going to track that stock and all our other operations until we basically have removed all the stock on the part. So now we'll go back on our next part, and we're going to, we'll cut another area on a part here, and we're going to do a thing called floor and wall. I'm going to use that to finish the big flat area, basically the parting line shut-off area there. We're going to pick him, and I just said floor and wall, and say we're going to follow around the outside of the part, something like that. And there you go. So it was that quick we finished that face on the part. And we'll continue going on here. So now, when we start moving into our next operation, need a couple more tools for our part. All right, so let's go and look for some tools. I'm going to get a 12mm end mill. Again, the same thing. There's a bunch of them in there. I know I'm going to use probably a 6mm in the front and maybe a 6mm ball end mill to do those blended radiuses, something like that. So there's a 6mm ball to go on our part. And this time when we create that operation, we're going to go back up in here and we're going to say mill contour. We're going to do the rest mill operation. And now we can see, pick the tools from our list. And maybe we'll go to semi-finish on this. And then the same thing. I can just window over the part, or you could pre-colorize the part. You can pick by color. You can pick by windows. You can pick by names. You could name different areas of the part if you like. Anyway, if you're going to go back on a part more than one time, I would generally, name that, give that name an area, or area name, I should say. There you go. Well, we did that. It only takes a second. Just pick that and rest mills, and so all the tools just contain to those surfaces. Of course, it's a fairly flat part, just a little bit of taper. And there we're going to go and generate and update our rest mill, because I never really said yes to it. Okay, there we go. We're going to generate. Everybody's good. We accepted it. All right, so we're going to go on. And like anything else, you just keep programming the part. So now from rest mill, let's go back and say we're going to do a little multi-axis on the part here. And in this case here, we're going to start using our 12mm end mill. We'll do the top area of the part. And with that, we do a thing called our variable axis, right? Because I know you guys are new to 5-axis, so I'll show you really just how easy this can be. So we're just picking the areas we want to cut with, and then we want to go back, and of course you need a tool. Make sure you got the right tool. Sometimes I forget how you want the tool axis to be controlled, and we're going to say normal to the part because that would be best. We're using a flat end mill. And then what's the direction of how we want that tool to look towards the geometry with that, and then which way we want to cut, and then say okay, and that's it. There you go. So that only took about 4 picks, right? We pick the part, pick the tool path type we want, and which direction, and now we could change that from number of step overs to, and there's different tool types: helical, zigzag, follow the periphery. We'll set a scallop height on the part, maybe 1/10 of a millimeter or something like this. That's good for a step over. Shouldn't let any scallops. So there you go, and you can see where we stopped around those little islands up there, so we need to go back and clean those guys up. If I want to extend my path off the part, right, so all different ways we can extend that, normal to the part, tangent. So I'm going to say I want to go tangent to the part, but before my arc I want to add an extra 8mm, right? So now watch what happens to our tool path. So there we go. We just get extensions off the part, so you can get a little drive onto the part. If you left I just did that in case maybe you wanted to leave more stock around the periphery of the part, right? You don't exactly just arc right in. You can come in a little bit flatter. So just to show you some options. All right. All right, so now we're going to go through and we'll cut around the outside of the part. We'll call this contour profile. So we're just going to take that 6mm end mill and walk it around the side of the part because it's tapered. There's no sense going in there and doing a 3-axis profile mill and having to do all the finishing work and our long tool path when you have a 5-axis. So those are predominantly flat. They're not doubly curved. And we just say generate, and it's that easy. You just pick the floor, and we just pick the walls, and X will follow the rest of the geometry through on the part, and there produced your 5-axis toolpath to clean that up. Okay, so now we're going to go and do a little more contour profile, but in this case we're going to do it up around the top, right? So we're going to clean up those little boss islands in there, and instead of saying automatic walls so it doesn't go out onto the side of our part, we're going to go back and just pick the top of those faces, because by saying it's context sensitive, it's just said the adjacent faces, so whatever I picked, it finds the adjacent face, and those become my walls. And there you go. Now we just got those guys cleaned up, so we should have the whole top of our part all cleaned up now. If it was multiple side passes, of course you can make multiple side passes, etc. And there's a whole other different surface types we could use. We could have spiral milled around them. So let's just do the contour profile on the front of the part now. So we're going to go through and pick that, and we're also going to pick the flat plane on the bottom. That would make good sense there. And we're going to go back in here and repick him because I wanted to pick him the first time, forgot. And then we're going to go back and instead of saying automatic walls, we're going to pick the walls that we just want to follow. Just those three around there. So we're going to drive that groove effectively on the bottom. And then I also may want to extend that a little bit. So I'm going to say automatically extend him, say 8 millimeters, another 8 millimeters out there. And there you go. It's that easy. So getting started with 5-axis, not difficult, very easy in NX. So you can see there we almost have our part finished. We're not in this too long, maybe 10-15 minutes, something like that. And here, let's go back and take a look at it. Let's say in 3D. All right, so, and there we go. We're going to clean off all of our stock blank. All right, that was our cavity mill. There we did a rest mill in the front. And oh, the only thing we forgot, we cleaned up that side. We didn't do our radiuses around the outside, and we didn't clean up the flat floor up there, but we easily could do that too. But let's go in here and show you how we can clean up those outer radiuses. You could do them in 3 or 5-axis. I'll show you this in 3-axis and streamline. You guys are kind of used to it to show you how easy this can be. And again, context sensitive. We look at that and say, just give me the connected blend radiuses, and they're all picked, so I don't have to have all this intensive picking to go on. And then that just takes a look at our directions. Which way do we want to cut? I'm going to cut in that direction. And what I want to do, I want to be just contact with it. And I can set scallops or a constant. In this case, again, we'll make oh, yeah, we'll go plenty small. And generate. And there you go. So now you have a super small step over. Should be polished when we come off. And there it is. That's how easy that is to do that part. Now let's go on and change our parts. So while we're in here, I'm just going to hide that first part. Now I'm going to turn on the finish part to do all those slots. Right? So there's all my program. I can update either one, turn either part on. And now we go back and we're going to machine all of our little slot geometry on it. Some in 5-axis, some in 2.5. So I'm not sure what the tool sizes were, so I just go through and do a quick measure. So I'm going to measure the slots. All right, so we go here and just pick measure. Oops, I pick that again. There we go. 1.5, so we'll make the tool a little bit smaller. All right, so let's go and create some tools. I'll show you how you create tools in here. So we'll just say we want to make an end mill. And we'll pick a spot to put it in a pocket, put it in pocket 9, and I'll give it a name that I can remember what it is, something like mill 3 or mill 5 millimeter, or mill 6 or something like this, right? So we'll say that's a mill, I forget what that was, 5 millimeter, I think, or 6. I'm not sure anymore. I think it's 5. We'll use a 5 for now. We can always go back and change it. It's that easy. And if it's too big, it'll tell us the tool won't fit. If it's too small, that's fine. We'll make multiple passes. So let's measure that again. It's 3 millimeter. There we go. So maybe I want to go back and edit my definitions of that tool. So I'll show you how that happens. Again, there's looking at the machine with all the way we see it with the pockets. And this time we'll give it a shank and a holder, that kind of stuff. Let's go ahead and define a shank for the tool. Because probably a tool that small would be a shank tool, maybe 12 millimeter, and it's probably 50 millimeters long, 35 millimeters, something like that. And then I'm going to rename him too. Instead of saying he's 5 millimeters, so I don't go using him somewhere else, and he's a 3 millimeter. There we go, 3 millimeter end mill. Okay, so there you've seen lots of edits, right? Not everybody's perfect. And here we go. So we're going to go create another tool. We're going to create our tool over here, maybe 1/375 millimeter, or something like that. And same thing, we probably ought to give him a shank too, because I know for sure you're going to need it. That would be a shank tool, I'm pretty certain. He won't be too long. We'll do the same thing, 35 millimeters, maybe by 12 or something like that. Yeah, maybe 12. There, better. Make that smaller too. 20 millimeters. And then the shank, same thing. If you want a shank, it'll build the shank. And in this case here, we'll use something like a 12 millimeter shank, and our shank length will drive down smaller to 50 millimeter. There you go. So there's two tools, and we can create them. You can create tools in the pockets where they belong in the machine. You can program the entire part that way, just underneath each tool. So here we go. We're going to go pick our part, tell us what our part is. That becomes our part, our new workpiece. In other words, our operation 2 workpiece. They all belong to that same machine coordinate system. They all have that same common piece of stock, right, for what's remaining on the part. And to do a 5-axis slot, you literally just pick the slot, contour profile, and again, we're going to extend the distances to drive the tool off cleanly. Make sure we don't let any burr there. Okay, and if we want multiple passes, I'll say I want to do multiple depths, and I say my stock depths maybe 7 millimeter or something like that. It looks. Again, you can measure what the height is in that total depth there. I'm going to say it's about 7, and we'll take maybe 2.5 millimeters or something like that, or per pass, or 1.5 millimeters, I guess. Oh, and it says, wow, no wall geometry. Well, guess why? We didn't have the right workpiece, right? So we go back, and if I pick that as the right workpiece, right, then it'll actually find the right parts for the walls. That would be better. So again, NX is a lot smarter than you. It kind of guides you right through it when you make those kind of mistakes when you're programming. You just go back and pick that, and there you go. So there you got some 5-axis roughing and with a finish path. How do we do those little slots on the side? Well, same way, nothing too difficult here. We just pick the part. We're going to go back, workpiece again, and then we're going to say we're going to do automatic walls and just pick the bottom of the slot right there. There's one, done. Okay. I'm going to say follow the part, so we clean it up on both sides. There we go. In and out. And then let's spin around and do the other side. Come in here. And there we go. Pick that slot face down there, zoom in. There we go. And then generate. So there you have it. We did the slots. We cut around the pockets. And we do the same thing. We complete a part with different work pieces, different stage models, of course. We can show you a change on that part. So if we change the original part, you'll see that both the operation 1 part changes, and stock will change with it and update it and transfer it to the next part, operation 2. No matter how many operations you have on the part, operation to the next operation. So here we'll go ahead and verify this a little bit, create the shop docs. Right, so we just output the shop docs. It was that quick. We just go up there and pick shop docs. And the way we're zoomed in on the part, it takes images of each tool path, right? So we could go through and there's your cycle times, for each operation. My post, so there's my 5-axis output for that. And now we're going to highlights of what we had seen. And this really covers our roughing capabilities in our 2.5D volume-based machining to our surface machining and rest milling capabilities. Then we have our automated 3 to 5 axis, right? So you can take all those 3-axis profile or finishing paths like that, and with a single click, remember we converted that to 5-axis. So I know you're buying a new 5-axis machine. This becomes, an easy way to get involved in 5-axis while you're on the learning curve to learn your additional capabilities of everything we can do inside a 5-axis. Along with streamline cutting, again, you can see how easy that was. You just pick the direction of your blend radiuses or fillets or edges, and then the cross directions, and we'll build that tool path, and that can be in 3 or 5-axis, as we had just shown with the converted to 5-axis. And then our intelligent 5-axis, again, as you've seen, is you can really just pick one edge in a surface, and then there's a lot of options to let you control your tool axis along with dynamic tool axis. Okay, let's do a little quick business review of the values we just seen with synchronous editing and milling. First off is it's easy to use single user interface, and studies have shown that users are more productive using a single user interface, and they're less prone to errors than when they move from system to system with different interfaces. And the model-driven process, it uses only one source to develop and maintain the downstream associativity that thus leads to increased productivity and efficient processing of engineering change notices or anything that needs to change after the fact that the parts were programmed, our drawings, etc. were created. And then model preparation time reduction. This really goes back to saying is where one of your biggest bottlenecks were, was reducing that time. That was the first item on the agenda. And we really have shown, I believe, that it takes us minutes rather than hours per job. And there you can see just a little matrix of the time factors going in there for what you're currently spending and just what the savings can be with NX over a single year's time or over a 3-year cost for job preparation in savings with NX. Okay, let's get back on track on our agenda. Let's take a look at the automated programming for doing the mold plates. Okay, here we go and take a look at feature-based machining, and again, it starts the same way. You get to see this. We're going to just open a part. So let's go back there, find our parts, just pointing Windows navigation, and we'll go to our core plate, and we'll change this to all of our, let's say a parasolid part, because that's the kind of part, so we'll look for all kinds of parts. There we go, picked him. And there comes in your typical mold plate, right? In this case, maybe an insert plate. And so you get a lot of those, a lot of holes, a lot of features. This one doesn't have a lot of holes, but it could be full of holes. Really doesn't matter. In that case, we set a machine setup again, just as we did before. In this case, we're going to go in and just pick, say, a machinery template just for 2.5 axis. Of course, you could do it as 5 axis, but based on what template we pick is based on the kind of features that would be capable of machining. The only thing we really need to do is tell it where 0 is going to be, your machine coordinate. Define who the workpiece is. So we're going to pick that as a workpiece, and I'm going to build a blank just to show you some other options here. So you could say it's a bounding box, and we'll just find this same size of the part, and you can drag on all the arrows or key in a value. I'll just lift it up so we have some face stock and on the part like that. There you go, we're done. Now all I have to do is say find features. So far this hasn't been too hard. So I just say find features, and then I'm going to tell it which way I want it to access the part, right? So first I'm going to find all the features on the work part, and then I'm going to tell it which way I want to define the tool axis, right? So in other words, if there were holes on the side of the part, you can only pick those, and that way, you know, it knows which ones it can access. That's basically, or which ones to find. So now we go back and say, look, go find me the features, and so it's searching, recognize the features. Everything that's in red is things that are going to be machined, that it could reach. Okay, so there we go. It was that simple. Say OK. There's all the different features. They're all highlighted. That's our access vectors, the arrows. All right, so you can take a look at each one of those, click through them, highlight them, whatever. All right, I'm just going to highlight the entire list. And now all I have to do is say, go create the feature process. In other words, create the operations to do that. And when I do that, how do you want to do them? I'm going to do them on a mill drill, right? And here we go. So I just do that. It's going through the tool libraries now and selecting tools, and it's creating the operations to do all of those features on the part. And so there we are. Everybody's done. If we turn around and take a look at this, you can see there's our holes, our slots, our stepped holes, right? There's some surface machining. All that stuff was done. So let's just go back in here and take these items and let's put them into our program now. Again, you could pick and choose the things you didn't want. You could just delete the things you don't want. You can reorder, like here I'm going to bring the facing up to the top of the part first, right? So you could reorder that way. Didn't show you that before, but that's how we move things around, just drop and drag. And then let's go ahead and generate these. So I'll go through and now generate the actual toolpath that created the operations, and then there's the generation phase which creates the toolpath, and then they'll be ready for post-processing. There they are. Everybody's done. So so far I don't think we're in this much more than about 3 minutes. And there we go. Now we can go ahead and verify the part. There's face milling, cleans it up, there's some pocketing. Of course you could change the pocketing, maybe use a bigger tool or something like this. And there's your drilling and chamfering. There you have it. That's it. All in about 4 minutes probably total time. So that's it. Feature-based machining. And once again, let's go back and review the things we had just seen, how quick and fast that really was. We were in there maybe 3 minutes for total time to doing the whole setup on that part and machine it. So as we take a look at the business value reviews for feature-based machining, is we can see is that the rapid programming for mold and die plates is we have really taken, again, this is the factors from your pain points that coming out that your current system's taking over 20 minutes to program the plate work per plate. And we look at that doing, as you just seen an example with feature-based CAM, we reduce that to 3 minutes. I mean, that's almost a 6 times reduction in programming time. Well, it doesn't seem like much in a given time or day, but if we look at that times the number of plates, the number of jobs per week, and again, at a typical rate, we have just a little cost factor chart down there, and it looks like from a savings point of view is, you're saving almost $22,000 a year just in time in programming the part, which is more than enough to pay for the entire 3-axis programming system from NX CAM alone. All right, back to the agenda. We're getting close to wrapping up here, so let's go take a look at the our integrated turning solution. NX CAM's turning is 4-axis out of the box, so we can do single spindle, dual turret, or dual turrets and dual spindle. So we start again, just like master model, you have a part, and we would do any job preparation on there that would be needed, and then we move into our setup where we add our blank or stock or bar stock, or this could be castings, whatever the case may be, and then we do our turning operations, and then we just literally go to our milling operations. Meanwhile, we're tracking the in-process work piece, so you see exactly what has been cut, what hasn't been cut, or what remaining material needs to be cut. So let's go see it live. We'll look now at turning. Same thing, we're going to open some parts, and we're going to open our sprue bushing. So there you go, same thing, solid body. We come back in, and now we're going to make a machine setup for it. Same as all, same procedure. So you get to see this procedure 3 times. So let's pick mill turn. And we pick mill turn, there we got our part. And now we need to, make some stock for the part. And we'd like to clean this up a little bit. You don't have a dual spindle, we just delete that one set of configurations inside of there. So there you go, we have a main spindle and turrets. Create some stock. We're going to use the cylinder command to do that. We're going to just say what's the axis we want the cylinder to be created, because it's a part we can make out of cylinder, not a casting. That's my axis. I'm going to flip the direction. And then where do I want my stock to be placed? I'll pick the center of the front of the part. And create them. So at this we could show them. And so there we got one. And I'm going to change his color, make them trans and change his color. So make them a little translucent, something like that. Maybe make them a nice peach plum color, something like that. That's nice, good. So now you can see the part inside the stock. And the next thing we're going to do, same as before, is we're going to add fixtures to our component. In this case, we're going to add a chuck. Now this could be more than a chuck. You could have a whole drawing of the machine tool, cross section. And you could actually load the 3D model for the machine tool if you like, especially when you're starting to deal with mill turns. Knowing the length of tools and their configuration is always handy. Thus a simulation kit comes in handy. Let's just put those two together real quick, right? So we just mounted the part to the chuck. No big deal there. Same as before. We just said add those 2 pieces and make them concentric. But we want to move our bar stock out for our part and our piece. Well, it really becomes easy. We can just literally double click on that and make it longer. So we just go that, maybe try 120 millimeters, see what that looks like. Of course, you could do a measure, etc. Nah, it's still not quite long enough. So what do? You just double click again. And what do? We change it. Another 15 millimeters or something. There you go, that's plenty. And now we want to add some stock on the face of our part, because another thing about NX is if there isn't any stock to cut on a part, you can't create an operation there because it says there's no stock to be cut. Right? We have our assembly. All right. And so now let's go and set this up. We're going to tell it who the workpiece is. This is all kind of the same. So you're getting to see the familiarity of NX. It's the same thing. We do a work part and a stock part, and you can have as much fixture components and things as you like. And now we need to tell it, where we want our spindle. So we'll pick him, and then we're going to pick facing operations here real quick. There we go. You flip our part around up to the top. So what you can see there now is that we know where and what material can be cut with the tool and the geometry we had selected. So let's create that operation of facing here. Show you that again. There's facing. We're going to use 80-degree diamond. And you can see, watch what's going to happen here. when we go back up and we select that, look at the brown line. It's kind of hard to see it's brown, but that's everything that that tool could cut. So let's go in and just say I want to cut the face. And so there you see there's the stock boundaries for the face that it's going to cut. And now we just go ahead and literally say let's cut it. But before we do that, let's tell it where we want, what we want to do with the tool when we're done. We want to depart the tool, and the kind of departure we want to use is we want to move off the face axially, then move up radially. So we're going to do axial to radial. We'll just start right back up there where our stock is. Like that, and then we'll go ahead and, like always, we generate. There's our tool. You can see the color changes on the part. It says it's been cut and the stock's been removed. The stock is the yellow. Of course, you could make that any color you like. It's just one of the system defaults. And so now we go to OD turning. The same thing as we go back up then. If we look at that, look what the path that already said I can cut. And of course, it's going back all the way to my chuck jaw because I didn't tell it the chuck jaw was a device component. Something it should stay away from, but I can do this. I just clip the path off, and we're going to tell it we're going to stop out there at that distance. And then when we're done, we're going to take it to our home position. So I'll just go back and say, let's go back to where we want our tool change position. And then we're going to do some drilling on the front of the part. This isn't a very complicated part. I know you had some interest in turning and mill turn, but so this way you get a kind of a good glimpse at what we do with turning. Again, it's very graphic, very interactive. I think it's pretty straightforward, really easy. We're just picking 3-4 icons at the most. We're going to create our tool, create our spot drill. I'm going to put it in station 2. And we got our 25mm spot drill. And now I want to go ahead and drill. And when I drill, I'm going to drill to my maybe my chamfer diameter if I want. So there you go. There's the operation again. You see it in green, what the material's been left. So let's say OK and create a drill. The same thing. We're going to go back and create our drill. And that's 12mm. Again, I measured the part before, etc., etc. And so we're going to create a 12mm drill. So I'll just say it's 12mm. Plenty of length. Say OK. And now the same thing. How do you want to drill it? Again, you can use a distance, a cross hole diameter to some specific point, etc. I'm just going to grab a hole. The nice thing is you get to see the tool itself, so you know about collisions, so you're not running into anything. And say that's how far I want to drill. And there you go. Now we've finished facing and turning the OD on the part. Of course, and we can go through and now simulate it basically, right? So we're verifying the material removal. This also is going to let us the same material, the way the part's already made, to go right into milling. So this may be really a big difference for you guys using Delcam, going from power mill. You'd have to take this part into power mill, and then you're not sure maybe where the stock is and how it was finished, etc. But here we literally just go up and tell it we want to create another operation. I'm going to turn off that piece of stock. So there's the 3D part. That's what we'd be milling to. Like that, and then I can go in and say I want to create an operation. Of course, what kind of operation do I want? I'm going to set my G50, G54, that kind of machine 0, right, for that. And so we're going to flip which way we want Z. Put Z up. That's my XY that I'm going to use. I'm going to give it a clearance plane. Right, we should probably do that because. So we use floor and wall again. Again, it's really pretty simple. There we pick our tool. And who's the geometry we want to work on, right? So we're going to pull down on that and say, look, it's going to be our work piece, right? That's the guy we want to use, our work piece. And how do we want to do it? Is it polar coordinates, X, Y, Z, rotation? And there we go. So we just machine that face. It's that hard, right? Change it to zigzag, maybe something like this. There we go. That's good. Oh, I remember I didn't do my clearance plane. I said it was, but I didn't. So let's go to my transfer rapid. Change that real quick. I'm gonna tell it what plane to use. We could use a clearance cylinder or bounding box or something like that. But I'll say 12mm and above that plane on the part over there, right? So I'll just always be 12mm above that. That's just saying it's going to link it to it. Right, that says it's always going to be associative, so if that part changes, that plane will change to the next cutting plane we use on the next part or a different part. And once again, NX is smarter than I am. We didn't build the tool yet. We didn't get one from a library. But there you go. That's how NX really helps you through that. Right? It's not going to let you say, oh, I created a tool path without a tool. You need to have a tool. So there you go. So now we got a tool. And press generate. There we got a part. That's good. Now we got to do is cut the other side of the part, so we'll just go right back over in here. We'll do another operation. Dun, 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 dun. floor and wall, same tool, now that we have a tool. And again, all I got to do is pick that as many floor and walls and whatnot I want. Change that one to zigzag 2 maybe. And there we go, just generate that one. And now let's move those up where they belong. They belong under the MCS mill. All right, so they follow that right coordinate system. And again, you just drop and drag them in place. You can reorder those features too that way. And that's it. That's how fast that is to do mill turn. There we are, we're finished. So now we can just do the whole 3D, run the whole program. Right, there's the milling portions of it. Right, so you see, and that's the remaining stock you can see was built on the part. So there's everything that would be in the chuck. Of course, we could verify this from the very beginning of the part with turning and all. So that was it, mill turn in about 8-10 minutes. So there you had it. You've seen kind of a quick mill turn demonstration on the sprue bushing. No, it's not a really complex part, but let me show you this in highlights with some things a little bit maybe more in detail, why spun outline is so important. So here we see a little bit more complex part that could be done from bar stock. It could have also been a casting. But in this case, to outline, no pun intended, the spun outline of the part, as you can see that not all turned parts are actually symmetric around. And so with spun outline, we calculate all these sections, and you can define as many sections as you want, are at different planes and specific locations. We calculate that based on your center line of rotation you'll be using, what that swinging space looks like, again, which really leads to a lot of safety issues. We know where that's large swinging volumes rotating, right? So we know how far we may travel in Z before those areas are there, and along with our clearance in X also to go in. So that's why we spun outline is done. Of course, if any changes happen to that part, the spun outline updates. So traditionally, you can say as we are turning in the normal 2-axis cross-section mode, it is just all integrated and associative to all the 3D models, including the stock. So here, a little bit more on turning highlights, just briefly. I'm not going to go through all of those. In fact, it's not all of the options available in turning, but it just gives you a good idea of the iconography or the graphical feedback and description we have. So when you select an item on the screen, if you recall, you've seen these pop-ups come up, so it's a good explanation. Let's take a look at the business values in turning. Really, you can look at all the above values up there, and we talk about a single user interface, any level milling 2 through 5 axis inside your turning environment like that. The ability to track always the remaining material in real time to see that's cut during operation, so you don't waste time on the floor with uncut areas. So for us, as we really see, is the advantage is clear. It's one interface, single maintenance cost. You're always on the same revisionist software through 2 through 5 axis milling and turning. As we'd say, is all of these advantages you currently do not have with Delcam. So we see the productivity will increase, the ability to utilize what you paid for in your mill turn equipment will be capitalized on, and we'll eliminate the at-machine prove-outs and uncut material areas. Okay, so let's take a look at what happens with the ECO notice. As you can see, with NXCam, we also have the ability to do model compare. So we can compare the difference between revision 1, revision 2, or really compare between two different parts and highlight the areas that have changed. So let's go in and see how we would use this inside of NXCam on a part that's already been changed to update not only your tool paths, but your assemblies, your setup drawings, or any other documentation that we've done inside of NXCam at this time. So it's really as simple as just going in and loading that new component. So here we're going to go in, and we opened our part, and let's go back and say let's browse for a part we had loaded. So we loaded it to preview it. So there we're going to select it. Now when we select it, you'll see it'll just instantly change here. So it just popped right in. Actually what happened in that background, it really replayed everything to do with that part, include all the synchronous editing. It marked those tool paths that need to be replayed. So there you can see they're all with that red symbol. It says, look, you need to go back and regenerate those because there's topological changes. And it's really just that simple as saying, okay, let's regenerate those. So now you can see it's going to go back and replay all of those areas of the part from the roughing on down. And then it's going to take a look at all of those change areas. And we're going to take a look at what happened with that tool path in that area, particularly with the slots and on the face milling. Those little bosses have moved. So there you see on the slots, a great example of that. It just literally added the additional passes for you. There's nothing else to do. The topology for the part have been updated, so all those tool paths have been done. You don't have to reprogram the part or make any other changes. So at this point, let's take a look at what happened also with our other part. Because everything is associative, we can look at our drawing files. So we made at least one simple drawing here as like a quick setup drawing, but of course these can be a lot more detailed and do in-process sheets, inspection sheets, etc. Again, from anybody's incoming data. So there again, we display update. It updates all the views, and there we have it. Okay, let's go back to our PowerPoint here, and you can see, what about that ECO notice? Well, let's go ahead and take a look at the business values that brings us for ECO handling. So the rapid change of revised parts in minutes versus hours, and these are all the benefits to this. It's all done in one unified system. I don't have to go to SolidWorks, to AutoCAD, or some other CAD authoring tool to make all of those changes that occurred to my manufacturing part. It's all there inside your CAM system. There's no searching for the right version for the parts and drawings. Again, all in one system. It's fully associative to all of those in-process manufacturing models, fixtures, and tool paths. You can preview the changes and find out what has changed on those 3D models with NX Model Compare. That's included in NX CAM. And again, all the associativity to the drawings. We can't mention enough associativity. It's really the core function of NX. We can remain associative even to anybody's CAD designs, whether they're SolidWorks, PTC, CATIA. Anybody's data we bring in, we have that full associativity because of master model with NX. And even you can change back and forth between revisions. So if you have to go back and remanufacture the part, and that time it was in version 1 of the part, or version 3 or 5, any of those revisions are available at any time. From a dollar and cents value, if we look at that again, we asked you again, these were your numbers. You told us that you produce approximately 3 ECOs per week. It takes you almost 3 hours per ECO. Again, we can see the costing factors. And again, you can see how NX really shines in the cost savings factor in terms of time, and again, which is really money, which is shop floor, which is production, which is also opportunity cost, where you can bring in more jobs just from the time savings alone. ECO savings in this case, it's well over $34,000 a year. So with that, let's take a little bit more and wrap up with NX. There you go, see, over 30,000 of your current process. So really, what makes a best-in-class manufacturing process? It really is a single driving source of master model. Typical layout here for a mold shop. You can see we can come right out of the tooling. Of course, that's available with our NX mold design product. You can have all of that capability, additionally, and more over your current process through this whole manufacturing work chain. With that, I'd like to say maybe we take a quick look at our business value review for everything we've seen today. We look at our milling, our feature-based machining. We also had about turning in there. We kind of pose that to you as you tell us the difference in turning, to have one integrated system versus two. It's really hard to tie down the numbers based on a simple part. But again, we look at ECOs. Just looking at those, and even excluding turning, we look at that. It's over a $75,000 saving over your current process alone in your first year. Just from time savings. So again, we're going to have this presentation for you for your review. You can question the numbers, you can plug in your own numbers and play. Those are active spreadsheets that go along with that. So with that, I'd like to say, to learn more about NX for manufacturing, you can visit us on the web today. With that, and I thank you for your time we spent with you today to show you NX CAM for manufacturing. Okay, let's go back to our PowerPoint here, and you can see, what about that ECO notice? Well, let's go ahead and take a look at the business values that brings us for ECO handling. So the rapid change of revised parts in minutes versus hours, and these are all the benefits to this. It's all done in one unified system. I don't have to go to SolidWorks, to AutoCAD, or some other CAD authoring tool to make all of those changes that occurred to my manufacturing part. It's all there inside your CAM system. There's no searching for the right version for the parts and drawings. Again, all in one system. It's fully associative to all of those in-process manufacturing models, fixtures, and tool paths. You can preview the changes and find out what has changed on those 3D models with NX Model Compare. That's included in NX CAM. And again, all the associativity to the drawings. We can't mention enough associativity, associativity. It's really the core function of NX. We can remain associative even to anybody's CAD designs, whether they're SolidWorks, PTC, CATIA. Anybody's data we bring in, we have that full associativity because of master model with NX. And even you can change back and forth between revisions. So if you have to go back and remanufacture the part, and that time it was in version 1 of the part, or version 3 or 5, any of those revisions are available at any time. From a dollar and cents value, if we look at that again, we asked you again, these were your numbers. You told us that you produce approximately 3 ECOs per week. It takes you almost 3 hours per ECO. Again, we can see the costing factors. And again, you can see how NX really shines in the cost savings factor in terms of time, and again, which is really money, which is shop floor, which is production, which is also opportunity cost, where you can bring in more jobs just from the time savings alone. ECO savings in this case, it's well over $34,000 a year. So with that, let's take a little bit more and wrap up with NX. There again, see, over 30,000 of your current process. So really, what makes a best-in-class manufacturing process? It really is a single driving source of master model. Typical layout here for a mold shop. You can see we can come right out of the tooling. Of course, that's available with our NX mold design product. You can have all of that capability, additionally, and more over your current process through this whole manufacturing work chain. With that, I'd like to say maybe we take a quick look at our business value review for everything we've seen today. We look at our milling, our feature-based machining. We also had about turning in there. We kind of pose that to you as you tell us the difference in turning, to have one integrated system versus two. It's really hard to tie down the numbers based on a simple part. But again, we look at ECOs. Just looking at those, and even excluding turning, we look at that. It's over a $75,000 saving over your current process alone in your first year. Just from time savings. So again, we're going to have this presentation for you for your review. You can question the numbers. You can plug in your own numbers and play. Those are active spreadsheets that go along with that. So with that, I'd like to say, to learn more about NX for manufacturing, you can visit us on the web today. With that, and I thank you for your time we spent with you today to show you NX CAM for manufacturing.